Actually, topic 3 are not many calculation, mostly concept and theory. So that's the reason it's become e-practical, no, e-lecture. So you all can actually read or even read, watch the video or read from the slide directly. All right. There is one part of the calculation important is the control valve sizing, which is end of the topic 3. I'll go through that later. And the control valve sizing is also part of the tutorial, right? So topic 3, right, instrumentation. We basically learn about measuring instrument. Measuring instrument here, you have 1, 2, 3, 4. 4 major types of, sometimes I call it sensor. I have to measure something, right? Pressure, temperature, liquid or flow rate. pH and compositions are not tested, so you can ignore this one, alright? Okay, and then pneumatic and electrical device, we have two types, controller and transmitter. Controller, basically we learn in topics 2 towards the end already. Still remember how many types of controller we have or we learn? 3 or 4. 4 types, right? We have what? Pi, PID, and PD, right? Those are the controller. Of course, different controller, you can use pneumatic or electronics to run or to operate it. Control hardware, you have control valve, alarm, interlock device. Only control valve will be tested. These two will not be tested, okay? Right, so this one is just a recap what we have or what we do for entire process itself, the PCI process itself. The first part, of course, we always read from the process. When we have disturbance, we measure by the device, send it to the controller, compare to the set point, control the final control element, adjust to adapt to whatever changes we have. This one is a generic and very common flow or the block diagram that we have. Today we're going to learn this part, the measuring device. Alright? Why is it so important to have this measuring device? Of course, we need, when we in the control system itself, we must have a sensor for us to display whatever we measure. Let's say temperature. If I want to know, I want to control the room temperature here, I must have a sensor to measure, right? So let's say a temperature sensor. After it's measured, it has to be able to display. Sometimes I need to record down all the temperature or the data that I have for whatever I measure. So after I do measuring and recording, right, I need to take some action. If let's say, remember we still have two types of loop itself. One is called open loop, the other one is called closed loop, right? This one you need to refer back to your topics 1. So for open loop, after we measure, whatever display is actually operator manually going to switch off. Let's say I measure the temperature, I see the temperature here very hot, then I need to turn on the aircon. For an open loop, the operator go and turn it on. For a closed loop system, whatever I measure is actually sent to the system, the control system itself, and compare to the set point, and then whether we need to take action to on and off the temperature in this lecture, let's say lecture hall itself. So the purpose of the sensor or the instrument itself basically is display, record, and give us different action, depends on the loop that we want to do, okay? And then you have a list of terminology here. If I tell you not tested, will you all read? Yes, right? I want to hear the answer, yes. So okay, basically, try to read and understand it because it's a concept that you all need. If I move to the next slide, you know what I mean, right? So all this, I just move to the next slide, but I wanted to highlight there are a few things, try to understand this, and this, because sometimes in work, people will ask you, what is accuracy, what is this precision? What is accuracy and precision, what's the difference? Yes, I think that's a very good explanation. Let me show you something. Alright, which one is accurate, which one is precision? This one is, let's say you got a target, right? If let's say everything that you aim at the target is very accurate, right? In this case itself, it's not accurate, but whatever the result or the aim that you have is actually grouped together. So it's actually inaccurate, but is precise. Okay? So for this one itself is inaccurate and not precise. So only this is very accurate and very precise. So accurate refer to if you have a target and then you hit the target same point. That is very accurate. Precise is you can reproduce the same result even though it's not at the same accuracy. So this is precise, this is accurate. Okay? So things like this are the examples of the terminology or definition that you all need to read and try to understand. Okay? For the sensor itself, it will test you more on the working concept or the examples of the different instrument. All right, so it's more important from this slide onward. Okay, but please remember to read also. I always encourage you all to read to improve your knowledge. Right, I want my students all work out here like wow, very knowledgeable. People ask you, wow, what is accuracy? Yes, I show the diagram. Okay, all right. So although it's not tested, please read. Okay. Instrumentation, we need to learn pressure, temperature, liquid, and flow rate, right? You may need to ask to draw the diagram, and you may need to ask to explain the working principle. So we will go through some of it one by one later, all right? Wherever applicable, you must also be able to describe the advantage or disadvantage of this measuring instrument. They are like, for example, sometimes why you use this instrument to measure the level, why I don't use other types of level measurement, things like that. I'll go through that one by one also. Alright, the first one is pressure, right? Pressure, we have this first, what we call it, the manometer. Alright, manometer, how does it look like?
The U.
I think you all roughly know, right? It's the YouTube, right? If I show you the slide, it looks like this one, the picture, okay? So basically, you apply a pressure here, and then you can also apply a pressure here, right? Process pressure means that if I connect, imagine just I want to connect this one to, let's say this is a pipe. I want to connect the front upstream at this point, and then I connect this at the downstream. It means that whatever flow rate through here, the pressure will drop, right? So I can measure the differential pressure. But if let's say I just apply a pressure and I make it open to atmospheric like this, whatever I measure here is actually the gauge pressure. So if you look at this one, before I go to the working principle, I want you to look at this. What is sealed column? What is open column? If let's say the tube here sealed, right, and this side is vacuum, and what you measure is absolute pressure. If the other side is open column, what you measure is gauge pressure. Can you all still remember what's the difference absolute and gauge pressure? Which one is bigger? Absolute, right? Because absolute you plus the atmospheric pressure also. So seal will give you absolute, which means that you measure not only the process pressure, you also measure the atmospheric pressure. Open means that both sides the atmospheric cancel out, so you only measure the gauge. The principle of working is the change in the pressure will cause the liquid to rise or fall in the tube or the column. So if I ask you for principle, this is the answer, all right? There are three common types of manometer. Although we have this, actually can break it down into three types. The first one I show you just now is the U type, and then you have well type, and also the inclined tube type, all right? So let's move on. U type, normally, as I said, you can measure absolute gauge or differential pressure. Absolute, you have to seal this side, but apply vacuum here. gauge, you open both sides to atmospheric. Differential, both sides connect to the process. The advantage is visual. You can directly see the measurement. But what's the disadvantage is there is no signal can be transmitted out, so you cannot use it for process control. Okay? Clear? Any question? No, move on. This one, well type manometer. What's the difference this one compared to the previous one? Huh? Only have advantage. Have a disadvantage also lah. But the main difference is actually one side of the tube is very big, right? The other side of the surface is very small. Why they want to do like this?
Hydraulic pressure.
Why? Huh? Yes, something to do with pressure. But the thing is, to be simplified, right? If you have a big surface here, right? When I apply the pressure, will the level here drop a lot? No, right? So only this side of the level will move. And whatever I move here, I can read directly. I don't need to minus it out. Let's say you compare to this one, right? You need to know this level, you need to know this level. Then you minus it out. When you apply a bigger pressure, this one drop more, this one move up. So you always need to read two sides to measure or to minus it out. But this one, when you use this method, right? This side, the level never change. So you don't need to minus out the inside. Whatever you read here, you can directly give you the reading of the pressure. Alright? So this is what we mean that it's single scale reading for the del P, which means that I can just read from the scale here without minus out whatever pressure on this side or the level on this side. The pressure still apply to the liquid level, but the level does not change because the surface is big. Alright? You need very, very high pressure to push it down significantly for you to show you need to minus out this level. If it's not, you can just read whatever reading here, and the difference of the height is the pressure that you want to measure. Alright? This is why you sometimes use whale type manometer. Alright? Okay, these are the principle, and sometimes I may ask you to compare. And yes? Okay, the other one is what? Inclined tube manometer. This one, similar concept to previous one here, right? But what's the difference is on the tube here. Why they purposely tube it in this way? Any reason?
Sensitivity.
Huh? More sensitive. Why? Why is it become more sensitive?
I can't remember.
Not true. When it's slide like this, doesn't mean the water will move fast, easier. The only difference, if you look at it, is if I make it vertical, right, my height is only this h, right? If I do it slightly like this, actually the entire height become longer. So the same pressure, but I can spread it to a longer scale. Let me repeat that. Let's say I have here 10 meter, right? But let's say make it slightly slanted like this. The entire length here become 15 meter. But the pressure does not change because the pressure still the H itself. But the same 10 meter now I can read for the 15 meter scale. So I can have more accurate. Instead I have 1, 2, 3, 4 until 10, right? I may be able to have 1.5 smaller scale and spread over longer scale over here. That's the reason it become more sensitive, right? Can? So if you look at this one, you just straight only, you only have one height. But this one I tilt to the side, the pressure itself is still this H. Because pressure still vertically, you have to measure. But my scale now actually longer. And how to get the length of this scale is actually H multiply cos X. Cosine X. If you want to get this one is 90 degree, right? So if you want to get this length itself is this multiply cosine X. And normally that length itself is longer than the H itself. And for a bigger length, same pressure, you can measure more sensitively. Okay? This here explain all the things. Disadvantage, I think for this one, can anyone advise what is the disadvantage of this pressure meter? Huh? Disadvantage. Horizontal distance. What's the problem with the horizontal distance? Yes, because these types of manometer is normally very bulky, right? So unless you have a very big process plant and you have place to put it, and there's another disadvantage, it's similar to the YouTube manometer. This one only visual light, you cannot transmit the signal also, right? So it's not no disadvantage, it just didn't show, all right? Okay? Let's move on. So we have three types. So remember, if I ask you to describe three types of manometer, please, the working principle and also advantage and disadvantage, try to understand it. This one is what we call barometer. Barometer is similar to the manometer, but the tube now is inverted. So tube is inverted and the open is placed into the reservoir. So it's basically similar to the U-tube, but one side is sealed and inside here is vacuum. So basically this one, like the pressure of the atmosphere on the mercury surface will hold the mercury and the tube. And the standard atmospheric pressure itself, the height is 760. So it basically, if I have any pressure here, atmospheric means that this total height is 760 because your top here is 0, right? It's a vacuum. So atmospheric pressure I want to measure is 760 mm. If let's say I apply additional pressure to it, then the level will move up. And sometimes you may need longer tube if you have a very high pressure, all right? The only difference compare barometer with the previous two is just one side is sealed and then inside is vacuum, right? So these are the concept. I think you all can read. Let's move on. The next one, as I said, we have four sensor or four measure variable that we want to measure. First one is pressure. The second one is temperature. Temperature is important, more important than the pressure. All right. But that does not mean anything. It's more important. In process itself, we always measure temperature. That's why it's more important. If we want to use pressure, we hardly use pressure in the process, but temperature we always use. Like in this room itself, we only care about the temperature, right? We don't care about pressure that much. So remember, it's more important. Temperature can be considered to be a measure the degree of the hotness of the object. It's measured the amount of energy on the molecular level, whatever. This one you can read. The principle of measurement, right? Super important. Okay? Alright? No, what I mean is like you have to know, right? If not, other time you woke up, people ask you what is the principle of the temperature sensor, you will not know, right? So it's very important. Okay? First principle is based on expansion, which means that anything expand, like for example, mercury in the glass thermometer, when it expand, right, we can measure the temperature. Bimetallic strip thermometer. I have two different metallic strip tied together. When the temperature change, right, one will expand more than the other one, so it will give me certain amount of reading. So that kind of expansion can also use to becomes my temperature sensor working principle. Change in state. This one state means that's the phase of the material. Like for example, the vapor pressure thermometer. If the thermometer itself originally is in liquid form, when the temperature increase, it changes it to gas phase, and the change of the gas phase will increase the volume, things like that. It will cause the temperature or the scale to move for us to measure. So change in state, example vapor. So you must know the principle like this. You must also be able to give you example, right? Change in resistance. This one, resistant temperature detector and thermostat. Productions of EMF. What is EMF?
Electromotive
Electric
force.
movement force, electron movement force. So this one, mostly on the thermocouple types of temperature sensor. Change in radiation, example is spirometer, alright? So if I ask you the principle, you give this side. If I ask you the example, you give this side, okay? We have more, yes, and all. More and all, right? Liquid phase in thermometer, liquid in metal, gas phase in this. This one, you need me to explain, or I think you all can understand, can read, right? So let's say liquid in the thermometer, normal, the temperature measure that we have. Liquid in the metal thermometer, which means the metal itself, the catch or the container itself is the metal. So when the liquid inside expand, it will move. All this working principle try to read gas also and the etc. Alright? These are the example. This one is what? Bimetallic thermometer. So you have two material attached to each other. This one has higher coefficient, lower coefficient. Higher coefficient means that when temperature change, it will expand more. So when it expands more, it tends to push the other side down. So when it's bent down like that, you can put a scale to read what is the degree of bending down, and from that itself you can correlate it to the temperature change in the room. Of course, scientists or somebody will in the lab, the manufacturer itself, they will test the material and they will test how many degrees it moves for certain temperature itself. Then from there he come up the final thermometer. So the working principle is over here. The concept here, sometimes you need to draw in order for you to explain better. Okay? Any questions so far? No question, huh? Okay. These are also the same. Let's move on. Alright. The third one, as I mentioned, is the liquid level, right? Liquid level means I have to measure the tank level. Liquid level, the working principle. Liquid level is the measure of the length in the vertical direction with respect to the Earth's surface. Alright? Whatever level we measure from here is the height. Okay? If I'm the liquid, anyone know what is my height? Huh? 148 ah? 148, 148 is like what? Okay, not 188. 117 something. Okay, so the level from the Earth's surface, alright? The types of level measurement 1, 2, 3, 4, 5, 6. We have 6 types. Please try to understand or able to explain it, alright? Sign means that the deep stick, I use a stick and I dip inside to see what is the height. Sign glass is in the tank. Sometimes we have a transparent glass on the side to represent the water level. Float is the one that whenever it's float, sometimes you can see the measure also. Weight, how is the weight to use to measure the tank level? Huh? Sorry? Yeah, density, or you just use the weight to calibrate. Let's say I have a tank, originally measured 1000 kg, and I have a level showing that for 1000 kilogram, the level is 1 meter. So if let's say I increase it to 2000 kilometer, the level has to be increased to 2 meter, things like that. So you prorate it, and there are some machine, they can use it directly to measure the weight and convert to the level. So weight can also be used, sometimes we call it load cell, alright? Electrical, of course, electricals, how does the electrical works in the level
You don't have the
measurement?
funny one.
So you put it there, okay, you know the level is very big. But electrical signal. Normally the electrical one, right, they insert the electrode that they insert under the water, they may have some pressure measure on the bottom. So the deeper you put, then the pressure increase, then they convert the pressure into the level, calibrate that. So electrical here is referring to after the physical, it will still convert into electric signal. Ultrasonic and radiation also, right? Actually, some of this level measurement, the working principle is towards the end at the additional reading material. If you all have time, you can refer it back. The only one that's I want to show you is ultrasonic level sensor. Okay. Ultrasonic level sensor is a non-invasive technique. Which means, what do these non-invasive techniques mean? When I measure the level, right, I don't need to go inside the liquid in order for me to measure. So I don't invest inside the liquid. So I does not introduce any foreign material into the process, right? Because it's a level sensor, means the liquid, I don't insert anything. What I do is actually I shine ultrasonic sound to the surface, and when it's reflect back, I have a receiver to receive, and based on that itself, I calibrate the level, right? If I look at the diagram, it is something like this. So you must have a transmitter or to sense the ultrasound to the surface, right? And then after that it's bounced back, receiver here can receive, right? What is the problem of these types of level sensor?
A lot of interference.
My hit object, okay, this is one, alright? Yes. And any other example? Hit the object, if let's say over here everything is very clear, and it's very common in chemical engineering, ultrasound will have this problem. Because in the chemical engineering, the water here will never steady, right? Because let's say it's a tank, I have a pump. So when the pump start move, the level start to move. So whenever the level, not a straight line like this, it keep moving, right? Whatever I receive may not be accurate, okay? And a lot of time, now the technology very smart. They can calibrate, they can fine tune. So ultrasound is still a very good level sensor compared to other types of level sensor, because it's electronic, you can send, and then you can mount it on the top, easy for maintenance also, because you don't need to all the way come down to the tank, inside the tank, alright? Okay, flow meter, second more important compared to the fourth, right? I have four types of sensor, right? First one is what I say important, just temperature, right? The second one is second one is flow, okay? Third one is liquid, then the fifth one is pressure, right? So flow measure. Actually, you all learn flow measurement during your UO1. Anyone still remember UO1? Right? UO1, you have orifice, rotameter, venturi, those are things, right? Similar, alright? So the flow of the liquid in the pipe determines primarily by the pressure that's forcing the liquid through the pipe. And you have basically restrictions flow sensor, obstructions flow sensor, and magnetic flow sensor. Restricting flow sensor, actually we go for obstruction first, then restrictions flow sensor, followed by the magnetic. The obstructions means what? The obstructions means that the operation by the effect of flow on the obstructions placed in the flow stream. So these are the two examples, rotameter and also turbine flow meter, right? Let's try to see rotameter itself. So the flow, go up from here, this fluid will move as per the, the velocity of it. So the obstructions is a fluid that rise vertically 10 column. So means outside here you can have the scale to read. Operating principle is flow of the water through lifting up the force, and then the distance, this one, I think you can read. It can use for liquid and also gases, alright? Okay, this one is for rotameter, and you should know that don't mix up. If I ask you to give example of obstructions flow meter, you don't give me venturi or orifice, alright? So the obstruction is rotameter. The principle is that the second obstruction flow meter is turbine flow meter. This one is the side view, right? So the water flow through here. This is the turbine. This one is the front view. If I look from this side, I can see like this. So when the flow through this pipe itself, the turbine start to move. And normally the turbine is made of this electromagnetic, it's made of this ferromagnetic property, which means that when it's rotate, if outside I have a coil, then I can start to generate some electric signal. So the faster it's moved, the more electric power that I generate the signal itself. So from there, I can know if I interpolate it to the flow rate itself, then based on certain certain electricity, I know what is the flow rate. So these are the entire working principle itself. It's very good or important to draw or explain with the drawing, easier for you to understand and easier for us to understand also. So two types of obstructions flow meter. Another one is the restriction flow meter. This one actually I dragged from the additional material to front here. So if you look at the back towards your lecture notes, right? These are the information I have. So when I put it in front means important lah, right? Okay. Working principle, restrictions flow meter, right? How many types I have? Restriction flow meter. How many types I have? 3 types, right? First one is orifice, venturi, and then there's another one we call it nozzle flow, right? This working principle, please read through it, and this one can recall from UO1 some formula, which means that the pressure and the flow rate has some relationship with it. And the types what we have, this one is venturi, orifice, this is the nozzle, right? So the flow through here, and then velocity change, pressure change. When the pressure change, I can relate it to the flow rate based on certain formula. Okay, that you can always refer to UO1 notes if you want. Okay, and what is the disadvantage of this restrictions flow sensor? By putting additional piece like this inside your flow rate, right? You actually introduce restrictions in the pipe that's cause additional pressure loss in the system, thereby reducing the flow rate, right? If we want, we try not to disturb the process, but in this case, if I use, let's say, nozzle restriction or orifice, I actually create additional pressure to the system, which means that when I buy orifice, when I use orifice as my flow meter, right, I need to size or I need to design a system to cater for additional pressure loss, because I know by putting this flow meter itself, I will create additional pressure. But sometimes I still use orifice meter for the flow measurement, mainly because of it's cheaper, easier to maintain. So you can see in industry, orifice meter is still a very common flow meter that people will choose to use. Amongst all this, right, the one that do not cause any additional pressure or less pressure to your system is the magnetic flow meter. Magnetic flow meter normally do not have any piece inside. It's actually mounted outside. They use the magnetic field to measure the flow rate inside. So magnetic flow meter outside, that's why it do not restrict the flow, it does not create additional pressure to the system. Okay? Move on. So head loss, orifice is higher, flow nozzle intermediate, venturi is lower. Cost, this one is cheaper, this one's in between, this one is higher. Alright? Alright, I think basically we finished all the four important measuring sensor: pressure, temperature, flow, and level. Okay, please read through that. The next item that we talk about is the controller itself. Basically, controller, we have two types, right? One is pneumatic, one is electric. Pneumatics means that the signal usually will transmit by pressure, and the pressure normally measure like between 3 to 15 psi. Advantages is why sometimes I want to use pneumatic instead of use the electronics one.
Safer.
Mainly because if the area have flammable or volatile product, so I cannot use electric. If I use electric, it can cause explosion, things like that.
Yes.
In that case, the entire control system in those rooms, I have to use pneumatic. Pneumatic means I only use gas to transmit my signal. If I want to on the valve or on the pump, I use air pressure to push it open. If I use the electric, what happens? The electric create spark, entire things will cause explosion. So it's safer. But disadvantage is it's very slow because I transmit air or the pressure always slower than I transmit electrical signal. So it's slower, especially the transmission lines are long. If let's say from here to there is near, if I want to transmit sometime like 100 meters away, the signal will get weak when you receive towards the end. Alright? Electrical controller have so many advantages. 1, 2, 3, 4, 5, 6, 7. So you can see nowadays a lot of people use electrical controller. Controller means that whatever I on and off the system, right? It only have one disadvantage, which is you have to meet the safety requirement for the hazardous environments with additional cost. It's not to say you cannot use electronic controller in the flammable area, but the controller electrical ones, right, you need to design for higher standard. There are certain standard can comply to combustions or the volatiles requirement. Alright? Okay. Very fast, huh? Is it faster than Chris? I think Chris also finished one topics in 1 hour.
Walao, don't remind me.
So
My brain fried.
a lot faster, right?
Orang dah macam like faham sikit tau. Yang tu
Okay.
is like totally
So
bila dia go through.
control valve, the important things here, right? There are a few calculations here. I think we can go through one by one. I will spend more time here, okay? But when I think this part is more important. Can I don't need to shout too much, right? Okay, this is quite important. There are some calculation at the same time. There are some concept. Okay, functions of the control valve. First of all, control valve is actually used as the final control elements, right? If you look at the entire process itself, what is this throttle mean?
Huh?
I regulate, right? I control. I use the control valve. If let's say control valve fully open means the flow can flow through. If I control it 50%, then I can throttle the flow. So this is why it said throttle or regulate the flow rate. Sometimes the control valve can use as a control variable. So these are the three functions of it. When an electrical signal sent to controller to an A pressure actuated valve, a current to pressure transducer is needed to convert to air pressure. What did this sensor mean? This sentence means. What did this sentence means? Over here, right, the control valve what types of control valve we have for this sentence itself? The control valve is actually A pressure, right? But I send an electrical signal. So if I send an electrical signal to control an A control valve, what do I need in between in order for me to be able to control the valve? I need a transducer, pressure transducer. So this sentence means if the control valve is the A control type, but I send an electrical signal, I must convert the signal into A. To convert that in order for me to be able to work. So I need a pressure transducer. Convert to 4 to 20 milliamp for this pressure itself. Alright? So control valve, not only electrical can control, sometimes A can control. Not only electrical signal can use to control, pneumatic signal also can use to control. So if the control valve itself is A, but I send an electrical signal, I need a transducer in between to convert the signal. This is what we meant for this sentence itself. Okay? Clear? Then? Move on. Still remember what is fail open and what is fail close? Remember? Fail open means I need to use A to push it down to close the valve, right? So when the system fails, do I still have A supply? You don't have, right? You don't have, that means this valve will open. So when the things fail, the valve will open. So when the things fail, the valve will open, the flow will flow through. This is normally when I need to make sure the downstream I have, let's say, cooling water to continue supply to the heat exchanger in order not to let the heat exchanger or the system to explode. So when the things fail, I want the valve to open to protect the downstream system. I will use fail open control valve. Alright, so if I ask you, I give you certain scenario, ask you to choose what types of valve to use, please remember this concept. The other one is fail close, which means that if the A supply to the valve suddenly stop, fail already, the valve will, because of the spring, move up, close the valve. So I want to protect downstream from sending whatever fluid to the downstream. I will choose fail close. The example we have in the tutorial is, if I have the wastewater, when the entire plant fail, no A, then the valve should close to prevent the wastewater go to the external to pollute the environment. So fail close is I don't want to send anything out. Fail open is when fail, I still want to send the fluid down the street system, depends on what I want to protect downstream. Okay, so you have these two types. The important is look at the valve position and the A supply. Okay, if the valve is on the top, you need the A to push, it's called fail open. If the valve is at the bottom and you only use the A to open it up, where it's fail is closed, so it's fail closed. Alright, this is how we read or understand this valve. Okay, so very easy, two types only, fail close, fail open, right? Okay, this one also has another name, right? What is another name for this valve? Huh? A open and A close, right? The A is not auto, it's A open or A close. So this one is use A to close. So this one is AC. This one is AO, A to open, AO. Alright, so you also, fail open has another name is AC. Fail close is also has another name is A open, AO. Okay? Alright. This one we explained already. The classifications of control valve, which means that if I want to classify the control valve, I can base on 1, 2, 3 category. First category is the action. We already explained whether it's fail open and fail close, two types. Second one is we can classify the control valve by size. Normally you have certain standard size like 2 inch, 4 inch, 6, 10 or etc. So those signs can tell you different control valve category also.
Actually,
And the other one is what we call characteristic. We have three types of characteristics of the control valve. One is called equal percentage, the other one is linear, the last one is fast opening. All these three related to your Fx and also the X. We will go through that later. Alright? So to classify control valve, three category. First one is by action, second one by sign, third one by characteristic. Alright? Valve sizing is very important. Still remember this formula. F equal to CV multiply Fx multiply square root of delta P divided by Sg. F is the flow rate, right? The flow rate must be in gallon per minute. So any flow rate give you in meter cube per hour, please convert to gallon per minute. CV is the valve size coefficient. This CV itself, you will a table will be given to you, and each of the size will tell you what CV or coefficient that you can use. If I have a lower CV, I should choose the higher valve size in order for me to comply the coefficient itself. We will go through that later. Fx is the fractions of the total flow area that is open to flow. Sg is specific gravity. Delta P is actually pressure drop over the valve. And please pay attention to the unit is Psi. So if I give you bar, you should be able to convert into Psi. 1 bar equal to how many Psi?
14.7. Kan? 14.7. Actually, I can't remember.
It's basic engineer you all. Huh? What? You laugh, so what's the answer?
Try cakap.
14.1.
7.
14.7, right? Wow, smart. Okay.
Smart lah dia.
Formula normally will be given.
Gurau je.
Huh? Which one?
Include video. This one so formal.
I think so. I think so.
Hello.
I can't
Oh,
remember.
that your friend yang tu.
Should be normally. But if I give you like this, you should know already, right? No need like give so detailed until each of these definition. So we beside this formula, there's another formula very important, which is this one, right?
Oh shit.
The first one is this F equal to CV Fx square root of delta P divided by Sg. The second one is delta P1 divided by delta P2 equal to F1 divided by F2 power of 2. Alright? So two formula is very important for you to size the control valve. Other than that, the other one is the CV itself. This one normally will give you in the table form. Which means that if the control valve is 2 inch, the CV is 55. Alright? So you must always convert the size into inches, and CV is just a coefficient without any unit. Right? Okay. The third category is actually by characteristic, right? All this not very important. You can read yourself. I want to bring your attention to this one. We have three types of characteristic for the control valve. First one is linear, second one is equal percentage, third one is quick opening. These all link to the Fx itself. What is linear mean? Linear means if I open the valve to certain position, right? Let's say I open, let's say the valve have a scale 1 to 100, right? If I open 20% of it, which means that the Fx will also open 20%. Alright, this is what we call linear. Let me repeat again. Linear means that you have to link between. Actually, you need to link between two things. One is what?
Okay, what?
Wait, I try.
You open all this.
Yeah, I saw, but I didn't press.
You need to press. Inside got pictures. What you want to see?
Normally we have this Fx, right? And also we have this
Oh
X.
yeah, someone was saying Oman for my birthday.
Fx means that the opening to the floor. X is the valve position. So for the linear one, right? fx and x are equal. Whatever let's say I open 20%, my fx is also 20%. Equal percentage means that if I open 20%, over here, the changes will be also based on 20%. I'll show you one table how we understand the equal percentage. Let's say from 40% to 60%, right? Compared to from 20% to 40%, both are changes of 20%. So your fx will be equal to the same concept. But linear does not mean like that. From 50 to 60, right, is actually the one have to open to 60 because 50 to 60, it already moved to 60 position. So the WAF is already open 60%. Okay? Quick opening is a little bit changes in the opening or the movement of the WAF position will cause the WAF to open very big. Okay? Let's look at as I mentioned earlier, right? Linear is fx equal to x. Alright? Equal percentage is the one that I want to show you, which is this one. Alright? This is for the equal percentage table. I think there is some mistake over in your lecture notes. Alright? First one is, let's say the x changes. X is what? X is actually the WAP position, right? So this one is actually the WAP position.
I don't know, but like this basically mean they call it star. That's why they call the park
Sinkhole.
because they believe that actually a meteorite. But then it's no what sinkhole is the thing soft one.
Yeah.
So, this one is WAP position,
Anyway, is that what's that?
right?
Then the sinkhole
But
and the goat.
X changes means the change of WAF position. And what I have here is from 10 to 20%. So the changes is how many percent? If I use 20 minus 10, 10%, right? 30 minus 10, also 10%. This also 10%. So equal percentage means if all these changes, right, my fx I can use the same percentage of change because 10 to 20%, the 10% change in the WAP position, my fx change 20%. So if I have initial 10, the number I should get after that final fx is 12. If I give you the first fx, you need to calculate the final fx, which is 12. How to get 12 is actually 12 minus 10 divided by 12 times 20%, equal to 20%. Then after that you calculate it. Always use this formula, fx minus fx final, this one is final, minus fx initial divided by initial equal to 20%. Can see, okay. So let's say I want to know the final, which is, I don't know, minus 10 divided by 10 equal to 0.2. If you put 10 here, you should get fx, which is equal to 12. Okay, so for the equal percentage, even I change from 20 to 30%. If I now have an initial of 12, what should be my final? So I use the final, which is I don't know, minus 12 divided by initial 12 time equal to 20%, because when 10% to 20% changes, right, my percentage of the fx is still remain at 20% because the delta x changes is 10%. So I have this 20. So over here I got 0.2. So when I calculate, my final fx is 14.4, right? Which means that for me to maintain, for me to increase from 20% to 30%, the fx has to increase from 12 to 14 if I want to size or calculate my control valve itself. Similar, if I have 30 to 40, the percentage of change is also 10%, right, for the x itself. And then from here, I know that my fx changes shall be 20 also. If I have an initial of 14.4, what I should calculate is the final fx. And from here, you calculate is 17.28. Okay? So based on the same concept, fx is important because in your equation, remember your control valve equation, you have this f equal to what? CV fx square root of del p divided by sg, right? So if I tell you the valve is an equal percentage, it's a characteristic, and I give you certain early position and move to certain position, and when I change it to, let's say, similar changes of the percentage in x, I want you to calculate the fx. You must calculate first before you sub in to find whatever new flow rate that you have for the control valve itself. Because fx is actually the control valve flow rate. This one will not change. This one depends on the valve position. This one we can calculate from the formula. Alright? Okay? So it's not always straightforward to give you fx equal to x. It depends on the valve characteristic. Okay? This one not important. Quick open, yes. This one, the f with the sub x, right? This one, the definition is here. Fx, right, is actually can be from 0 to 1. The earlier definition of Fx is here. Fractions of total flow area that is open to flow. So it means it's open to flow. So let's say if 1 means that what? Fully open or fully closed?
Open.
When Fx is 1 means it's fully open. Because the total opening, total area of the fractions of the total area to the floor is 1, fully open. You open everything, let the flow to flow through. 0 is fully closed. Alright? That's why you have this Fx in between of 0 to 1. Okay? This one is the stem position. X is the stem position, the valve position. Sometimes you can imagine the valve, right, has to operate from the top. So on the top I got a stem. So when this stem I move, the opening inside the pipe, the valve will turn also. So when I turn to, let's say, 50%, right, the valve may not open 50%. It only opens 50% if it's a linear sort of valve. If whatever I open, it has to be the same. But based on certain percentage equal 1, right, you have to use a formula to calculate to know what is the valve opening. And that valve opening itself will affect the flow rate. And that flow rate can use this formula to calculate. Okay?
Check grammar.
And I want to show you this one. The last one is actually, the third one is quick opening. The relationship between Fx and x. Fx is the valve opening, right? The fractions of the valve opening. This one is the stem position. So the relationship is based on this formula. So you have 3 formulas. Fx equal to x. The second one is this one based on the table. And the formula I give you over here. Then the third one is this one. Alright? And from here, in terms of the chart, this one is linear, this one is equal percentage, this one is quick opening, alright? Not very important, it's just a concept. The more important is the calculation. And as I say, the control valve, right, equal percentage, you have generic shape like this. Linear is sharper, the quick opening is like this. So if I move the stem down very quickly, it will close and open very fast. This one is, if I move it up and down, right, the flow more equal and smoother. This one is very linear. All this is just a very generic concept. You need to do some study or research to really link the flow to it. It's just to give you, if you want to understand what is equal percentage, linear and quick opening, the valve look like this. The stem is on the top here. What we say, the stem is on the top. So sometimes the stem move up or turn different position, your valve will have different opening. And then the fraction of this opening is the Fx. So when all these things move up, right, the fractions of the opening become 1. So the Fx represent whatever opening that we have. The stand position is the one X on the top. When I control the valve on the top, I will move the valve to certain position. Alright, this is the importance calculation for the valve sizing. Okay, this one I think we went through during the tutorial also, right? You need me to go through again?
No.
I think you're tired already.
Yes. So break.
Okay, I'll do this one next week because this one is important. Next week I'll go through with your tutorial or revision on this topic before I move to topics 4. Topics 4, there are 2 important parts. First one is the electrical part. Second part is the logic diagram or the logic gate plus the you all keep talking, I cannot remember. Logic gate plus the binary, the numbering, okay? Alright. That's all. I will see T01 next Monday for Q2 tutorial, and also I think 06